part in my previous video. Here I'm just going to do the B part. Okay, let's look at the question. The B part of the question is asking replace the BJT with its T model neglecting RO and analyze the circuit to determine the input resistance Rin and the voltage gain VO over vsig. Now let's see how we can do that. Okay, first let's see what is the circuit is gonna look like initially. So if they say this is circuit determiner. Okay, so this is for this one we are gonna draw the AC equivalent circuit, because when they say T model is like small signal model, that is AC voltage, AC signals. So in the part A we did for the DC signal. For DC signal the capacitors act like a open circuit. For AC signal the capacitor become a short circuit. So it means this is going to become like a wire connected to it. So if we do that, then the equivalent circuit is going to look like this: plus minus, this one connected to the ground, and here we have 10 ohm resistance, and then here we have 10 kilo ohm resistance connected right here, and this one will be grounded. This plus 9 voltage will be grounded in the AC model. So this 20k ohm is going to be grounded, and we have another 20k that will be parallel to this 20k, and we have the BJT after that. And this 9 voltage is going to be grounded as well, and here we have 2k ohm resistance, and there's a connection between this and this. There's a wire. That one we can just draw like this, that is before 2k. Okay, this is how the circuit is going to look like, and here we have the V output. Okay, so this is the equivalent model. This is like AC voltage. Like when they say T model, that is for the AC voltage. If they say hybrid 5 model, that's for the AC voltage. If they say DC, then there we had to open these two capacitors. So once we open that, the equivalent circuit for the DC model. AC model, we make it a short circuit. Okay, that's all you have to know. And this one is 10k right here, and this one is 10k right here. Other than that, nothing else to worry about. So this one is called vsig after we open this, and this one is called vsig. And this is how the circuit is going to look like. And now we can go ahead and simplify this circuit furthermore by looking at the parallel resistance. Here if you look at this one, this 20k, 20k, 2k, these three are parallel, so we can combine them together and make it just a one resistance. So if you do that, then this circuit is going to look like this. We are going to have this voltage vsig right here, and R6 remain the same, and then we still have the 10k, and the BJT is right there connected to the ground here, and bottom part have this resistance connected to the ground, and here we have a wire in before the 2k, and this 20k, 20k and 2k, we can combine all of them together and say the equivalent model is 2k parallel to 20k parallel to 20k. Okay, so this is the equivalent resistance, and if you solve for this equivalent resistance, parallel basically you can find out the parallel equivalent by 1 over R equivalent is equal to 1 over 2k plus 1 over 20k plus 1 over 20k, and you solve for the R equivalent, and you will end up getting 1.66k ohm resistance. Okay, so that is that. or if you wanna try the shorter method, you can do 2 by 2, like you can take 2 at a time. So if you take 2 parallel circuit, the equivalent resistance is 2 parallel resistance. The equivalent resistance is product of sum. So 20 times 20 over 20 plus 20. You find the equivalent resistance right here, and then you parallel that one with this one. So this one times this divided product over sum. This one times this over this one plus this. You find the equivalent, you will end up getting this. Okay, you can do in 2 ways. Either way you will get this one. Okay, and this is where the V output is there, and then 10k is there, 10k, and this is our simplified model. Now we can go ahead and represent this one in T model. In T model, nothing different. Like if you see collector, base, and emitter in the T model is exactly that. Only thing is we just remove the BJT, and if the RO is there, then we put it parallel to whatever we have here. But if there is no RO, then we don't have to worry about it, but only the emitter resistance will be parallel to this. Okay, other than that, nothing else will be different. And also uh, the collector current, we replace that one with a GMV5. Instead of IC, we will put GMV5 for it. And other than that, nothing else will be different. Now let's go ahead and draw the equivalent models. Okay, T equivalent. So instead of IC current, we put GMV5, and this one connected to the ground, and this is where the meeting point. This is where whatever in this side is the base. In this one we had the vsig and the rsig, and here we had this is base, and in the base to emitter, the bottom part is emitter, there will be a resistance in between that is called RE, and the 10k ohm will be parallel to that. Resistance will be parallel to that, and the equivalent resistance we calculated before, 1.66k, that will be right here, and the voltage here is called VO, and then the voltage here is the base voltage, that's VB, and the voltage between the VO and VB is the one is called V5. Okay, and that is basically it. Now if you look at this one, the only difference is it's gonna look exactly the same. You see, except the T model is like exactly the same. Only thing different is instead of IC current we put GMV5, and also we put a emitter resistor that's not clearly visible in this diagram, since we have the BJT, but when we put a small signal model we mention that emitter resistor right here. Okay, so that's the difference. Now from this one we can find whatever we need to find. Here the what we need to find is we have to find out the input resistance. Input resistance is nothing but like if you think in terms of Ohm's law. Ohm's law says V is equal to I times R. Therefore, R input should be equal to V input divided by I input. The input current should be the current going here. This one we can call I in. This is the input part of it. The base part is the input for the BJT. So I input, and the V input is whatever the value right here. Okay, so if you calculate VB value, base voltage is the V input. Okay, so we have to find out VB. We can also say this one as VB over V in as well. VB over IN. And we have two unknown variables. Let's see what is provided to us. Do we have anything provided? No. So we have to calculate some of the term. We can use part A calculations to deal with this. In part A, we calculated GM, RE, and R5. It might be helpful here. Let's see if it's. First, we can start with VO. So this one we can mention, this is the T model. This is the T model equivalent of the circuit we have, and they ask for the T model as well. So that is this is the diagram for the T model and VB. Okay, so we have to find out the I current, I in current, and also we have to find out the VB resistance, VB voltage. Okay, if you look at this circuit right here, if I take VB and minus this V5 voltage and minus this VO voltage, that would be equal to 0 according to KCL. If I apply KCL through this one, VB minus V5 minus V0 should be equal to 0. Okay, we put VB a plus because it's plus to minus right here. Okay, so this one also equal to VB is equal to V5 plus V0. So if you calculate V5 and V0, then that is the equivalent for VB. Okay. Now, is there any way we can calculate the VO? To calculate the VO, we can try to find, okay, here we have 1.6K, 66K, and here we have emitter resistance. And V5 is right here. E is equal to I times R. We don't know the I. 10K and RE is parallel. 10K and RE are parallel. And in the A part, I think we did, in the A part, I found out RE to be 14.5. So let's mention that one here. In the A part, I found out the RE to be from part A. We found out the RE to be 14.5 ohm resistance. And if you compare, when we have 14.5 ohm parallel to a 10K, the parallel, okay, 10K, if you take 10K parallel 14.5, 14.5 is the smallest values, and when you have parallel resistance, the equivalent resistance will take the smallest value. So here this is approximately equal to 14.5. okay, we can say this is equal to 14.5. so the equivalent resistance right here is 14.5. okay, so we can, this is 14.5, then this one is 1.66K, and we have V5 right here. So the VO is basically this 1.66K according to Thevenin's theorem. 1.66K times the V5 divided by the equivalent resistance right here, that is 14.5. okay, and if you simplify this one comes out to be 114.48 V5, because we don't know what is V5 is, but we can express the V output in terms of V5. So from that one, we have this one unknown variable available to us, that is V output is available to us, and we just so it means we can calculate the VB right there. VB is going to be just addition to 1 V5, and we know that VB is equal to V5 plus VO, and we calculated VO to be 114.48 V5, and 114.48 plus 1, that's 115. 115.48 V5. Okay, this is our VB value. Okay, but let's see what else we need. We are doing this one because we need to find out the R in resistance. That's what the question is asking for. The input resistance, that is VB divided by I in. So we have the VB expression, and let's see what is the I in expression. So I in is the current, the base current, and collector current and base current enter this node, and that is the current exiting through this node right here. So we can say, if I apply KCL, I in plus this GM V5 should be the current exiting through the emitter, that is V is equal to I times R. If we express this one in terms of Ohm's law, V is equal to I times R, then therefore I is equal to V divided by R, and the voltage right here is V5, and the resistance right here is RE. So this one should be equal to V5 over RE. Okay, so we are looking for expression for I in, so I bring the other terms to the other side. So this is going to be V5 over RE minus GMV5, and here we can take the V5 common. That's going to become 1 over RE minus GM, and V5 and the RE value from the part A question. From part A we have that is to be 14.5. So plug that one in right here, 1 over 14.5, and we also calculated the GM in part A as well. From part A, I mentioned here, from part A, GM is equal to 68.3 milliampere per voltage. So plug that one in, minus 68.3 milli, and calculate this one and multiply by V5. You will end up getting 0.466 V5 milliampere current. Okay, now we have the good thing is we have both of them multiplied by V5. So when we put it in this equation, R in equation, V5 cancel, and we find out the input resistance. Let's go ahead and do that right now. I grab the equation, R in is equal to VB divided by input current, and VB we calculated to be VB is 115.48 V5 divided by the input current, that is 0.466 V5 milliampere, 0.466 V5 milli, and V5 cancel, milli becomes kilo when it's go to the top, and then if you solve and simplify, you're gonna get approximately 248 kilo ohm resistance. Okay, that is the input resistance. Now the next thing we have to find out is the gain. Gain is given by V output over vsig, and here we have the output already derived. We found out the output to be this 114.48 V5, but we don't know the vsig. Okay, but here we can take advantage of the voltage divider by voltage divider by using this. We can also say we can multiply top and bottom by VB. So VB over vsig is equal to VB over vsig multiplied by VO over VB. This is exact same thing, like VB. If you multiply VB cancel and you get this one back, but we are using this one because since we don't know vsig, but we can find out VB over vsig, because here we have vsig and this is our, okay, let's look at in the equivalent model, T model. So VB is right here, vsig is right here. VB over vsig is the voltage divider, that is R in over R in plus R6. Okay, so if we do that, then this VB over V6 part will be replaced with this voltage divider, that's R in over R in plus R6. Now we have all the known variables because VO is already there. VO we calculated to be 114.48 V5. So this is 114.48 V5 right here, and then VB we already know, that is 115.48 V5. Okay, and R in value we calculated to be 248K, and R in the bottom 248K, and then R sig is readily available to us, that is 10K. 10K multiplied by 114.48, and we can cancel the V5 and simply write this 115.48. You calculate this one, you will end up getting the gain to be 0.953 voltage per voltage. Okay, so they ask us to find out the input resistance, and VO over vsig, that's the gain. We found out both of them, but we are not done yet. Like, it's better to give the gain in decimal. Voltage gain in decimal is would be the final answer. So we can say voltage gain in decibel. The voltage gain in decibel is nothing but 20 log 10, and you plug this value 0.953. Let's put the expression first. 10 VO over vsig. In this case, that is 20 log 10, 0.953. Calculate this one, you will end up getting negative 0.418 decibel. So the gain in decibel is negative 0.418. And that's it for this video. I hope you guys found this video helpful. Thanks for watching. Don't forget to subscribe my channel. See you guys on my next video.